to understand the concept of Nyquist stability criterion, let us see some of the example problems. The first problem statement goes like this. Draw the Nyquist plot for the system whose open loop transfer function is given by gh of s is equal to 1 divided by s into s plus 5 and find the stability of closed loop system. So in this problem, open loop transfer function is given, that is gh of s 1 divided by s into s plus 5. We need to draw the Nyquist plot. From that, use Nyquist stability criterion and investigate whether closed loop system is stable or unstable or marginally stable. Let us start. For in Nyquist plot, we have to take Nyquist path. Basically, Nyquist plot is the mapping of Nyquist path from S plane to GH plane. So what will be the Nyquist path for this particular problem? Now if you look at the open loop transfer function, it is type 1, which means we have one pole at origin. So if you have one pole at origin, then what will be the Nyquist path? So Nyquist path is like this. We have S plane. So at origin I have a small semicircle, that is from we have from that 0 plus to plus infinity we have one path, and plus infinity to again there is a semicircle with the radius r tends to infinity or e power j theta. Theta can be taken as plus 90 to minus 90, and this path 3 is having minus infinity to 0 minus, and as I said, this is a path 4 minus 0 to 0 plus. So when you take these four paths, map into GH plane, that will be the Nyquist plot. Let us see how to do that. So one by one we'll do. So first we'll take the path 1. What is path 1? In path 1, the frequency omega is varying from 0 plus to plus infinity. When you map it, which is nothing but the polar plot. So we'll see how to plot the polar plot. So transfer function is available, gh of s. Therefore, I'll substitute s is equal to j omega. Then gh of j omega is 1 by j omega into 5 plus j omega. Then we can write the magnitude and phase angle expressions. So without writing magnitude phase angle also, we can prepare the table because it is a minimum phase transfer function and there are no zeros at all. Now, so when you prepare the table, so omega for various values and magnitude and phase angles. So in this case, I am taking only 2 entries. You can also take the 4 entries for better purpose. So omega 0, what will be the magnitude? It's a type 1 system, magnitude is infinity. Then what is the phase angle? The phase angle is minus 90 degrees. Then when omega is infinity and magnitude is 0, so when you look at this, we have minus 180 degrees phase angle. The in between also we can take the values. So we will have having for lower values of the frequency minus 90 plus something, and at higher values of frequency it will be 189.9, which means so my entire polar plot will lies in the third coordinate from minus 90 to minus 180. So that we can easily sketch like this. This will be the polar plot. This is starting point omega 0, and it is increasing like this, it is going to 0. When it is approaching to 0, it is touching minus 189 degrees. Now, so this is the polar plot. This is a mapping of path 1. Now what is path 2? In Nyquist path, path 2 is defined as r e power j theta, where radius tends to infinity, and angle is of course plus 90 to minus 90. When you map that into the GH plane, it is going to be one semicircle or more number of semicircles with radius r tends to 0. Therefore, we can simply ignore it, or it can be taken as a one single dot at the origin. So I can take that dot. This is path 2. Now coming to path 3. What is the definition of path 3? It is from minus infinity to 0 minus, the omega is varying, which means when you map this into the GH plane, it is the inverse polar plot. So inverse polar plot is the mirror image of the polar plot, where the direction should be continuous. So polar plot is available. You just make the mirror image. Which means what? It is in third coordinate, that will be the second coordinate. The mirror image, the symmetrical about the x-axis. So you will be having like this, and the direction is away from the origin, because I need to have the continuous of the direction. Now, what will be the path 4? So, in this case, you will have path 4 because there is one pole at the origin. Then what will be the equivalent mapping into GH plane? When you map path 4 into GH plane, then you have to remember certain things. The first one is, so how many number of poles we have at origin? We have one pole. Therefore, the resultant will have only one semicircle. And what will be the starting point of the semicircle? Starting point of the semicircle is the ending point of inverse polar plot. Just now we have seen the inverse polar plot here. The ending point is this, that is at plus 90. So from plus 90, it should go to the minus 90, which is the starting point of the polar plot. So this is what, again I know what will be the direction of the path 4, it is always a clockwise direction. Therefore this is starting point, this is ending point, I am taking the clockwise direction with the radius r tends to infinity. This is the mapping of path 4. So we already seen 1, 2, 3, 4, all 4 paths. When you combine, then you will be getting the Nyquist plot. So this is what the Nyquist plot is, you can see. So this is a path 1, it is coming from infinity to 0, and from again 0 to in plus 90 degrees, again it is infinity, and we have with radius r tends to infinity a semicircle. So once you have Nyquist plot, then how to find the stability of the system using Nyquist criteria. The Nyquist criteria says that simple formula z is equal to p minus n, where z is number of closed loop poles that are lying in right half of the S plane. P is number of open loop poles that are lying in the right half of the S plane, and z is n is number of encirclements around the origin. The whole and sole purpose of the plotting Nyquist plot is to get n value. Then how to get the n value? Now let us take the complete Nyquist plot here. Now critical point is minus 1 plus j0. So generally Nyquist plot is drawn on real and imaginary axis plane. Though it is GH plane, but again we have real and imaginary. But polar plot in polar coordinates. The plot is same, the coordinates are polars when you take the polar plot, but when you take the Nyquist, but the coordinates are rectangular. The path will be same only. So in this plot, now I am taking on a real axis, negative real axis. In polar it is minus 180 degrees. So what is the critical point? Critical point is minus 1 plus j0. So from minus 1 plus j0, you draw the line towards the left side. So when you draw towards the left side, see whether this line is intersecting the Nyquist plot or not. So in this particular case, so this line is not intersecting the Nyquist plot. Therefore, how many number of encirclements? Number of encirclement n is equal to 0. So n is equal to 0 is information from the Nyquist plot. Then look at the open loop transfer function. It is 1 by s into s plus 5, which means there are no poles of open loop transfer function lying in the right of the S plane. So P is 0, n is 0, z is P minus n, so z is 0. So z is 0 indicates there are no closed loop poles which are lying in right of the S plane. Therefore the closed loop system is stable. So this way we can find the stability of the system. Let us take another example. See how can we plot and how can you find the stability of the system. The problem statement goes like this. Draw the Nyquist plot for a typical control system whose open loop transfer function is given by gh of s is equal to k by s into s plus 2 into s plus 10. And find the range of k such that closed loop system is stable. So in this case, I need to find what will be the k value, so the system will be in the stable region. This information we can obtain in different ways. The first method is RH criteria. Using RH criteria, we can easily find out what will be the range of k. And using bode plot, also we can find out what will be the k range. And using Nyquist plot also, we can easily find the range of k where the system is stable. So if at all you have the solution of characteristic equation, from that also you can find out the k value. So but what is advantage with the Nyquist plot? The advantage the Nyquist plot is not for the simple transfer functions. If at all, if you have non-minimum phase transfer functions, or if you have any open loop poles which are lying right off the S-plane, then we can use the Nyquist plot very easily. So this case also we can easily find out what is the K range. Now, so look at the transfer function. It is a minimum phase transfer function and it is type 1 system. There are no zeros at all. Now, if you have type 1 system, the Nyquist path is this. So we have 4 paths. One is from 0 plus to plus infinity, again from plus 90 to minus 90 with radius r infinity second path, and minus infinity to minus 0 third path, and minus 0 to plus 0 is a fourth path. So we know that the Nyquist plot is nothing but the plotting all 4 paths into the GH plane, where this Nyquist path lies in a S plane. So we'll take the path 1. We know when you map the path 1, it will be the polar plot. So we need to draw the polar plot. Take the transfer function. GH of is K by S into S plus 2 into S plus 10. So directly I can take the angles as well as the magnitude from the transfer function itself. So omega is 0. What will be the magnitude? It is a type 1, therefore it is infinity. Then when omega is infinity, the magnitude is 0. And phase angle, when omega is 0, the phase angle is, it is type 1 system minus 90. And there are 3 poles in the system, therefore when omega is infinity, it is going to be minus 270. So starting angle is minus 90, ending angle is minus 270, starting magnitude is infinity, ending magnitude is 0. So with this information we can easily sketch the polar plot. Look at that, when you take the polar plot, the starting is minus 270, it is coming from infinity and it is going to 0, but while it is going to 0, it is crossing minus 180 degrees line, and also it is intersecting the, it is touching the minus 90 degrees line when it is reaching to 0. So this is what the Nyquist polar plot. So this is the polar plot, mapping of path 1. What is mapping of path 2? We know that mapping of path 2 is 1 or more semicircles around the origin with r tends to 0, which can be ignored. And what is the mapping of path 3? It is an inverse polar plot where the direction should be continuous. So we know this is the polar plot. Then when you take the inverse polar plot with respect to x-axis, it should be. Then this will be the inverse polar plot. The direction should be away from the origin. So whereas for polar plot, it is coming towards the origin direction, it is away from the origin. So this is a path 2, path 3. Then what will be the path 4? So when you take the path 4, again look at how many poles are there at origin? 1 pole, therefore 1 semicircle. The second point is where it needs to start, the ending point of inverse polar plot. So what is the ending point of the inverse polar plot? So we already know that the inverse polar plot ends here. That the polar plot is, inverse polar plot ends here. So from polar plot starts here. So what is the path 4? Path 4 starting point is the ending point of inverse polar plot. The ending point of path 4 is the starting point of inverse polar plot, so that the entire direction is continuous. So I can draw like this now. It is at plus pi by 2 and it is going through the right side, and because it's a clockwise direction, it is going back to here, the starting point of polar plot, which is at pi by 2. So this is the complete Nyquist plot. Once you have the Nyquist plot, then you can find out the number of encirclements. So to find the number of encirclement, look at where is the critical point. The critical point is minus 1 plus a0. So at minus 1 plus a0, you draw a line toward the left direction and see that any encirclements for this, or any intersects of your Nyquist plot with the line which you are drawing from minus 1 plus a0 towards the left direction. Now it is very clear there are no intersections, then I can say n is equal to 0, which means this polar plot, this Nyquist plot is not crossing or the number of encirclements around the critical point of this particular Nyquist plot is 0. So you know that from open loop transfer function there are no poles in right of the S-plane, P is 0, number of encirclement n is equal to 0, then Nyquist equation we know z is equal to p minus n, the z is going to be 0. Since z is 0, I say number of closed loop poles that are lying in f of s plane, or the number of poles that are lying in right half of the s plane is 0, my closed loop system is absolutely a stable system.